Good morning, ladies and gentlemen. My name is Samar and I'm delighted to be here today to speak to you about the fascinating world of superconducting quantum computing. In this presentation, we will explore the principles, design, and measurement of superconducting quantum circuits, as well as the current research progress and development trends in this exciting field. Before we start, I'd like to talk about a vibrant and dynamic community called Dora Dōjō. Dora Dōjō is an open-source knowledge community focused on cutting-edge technologies such as encryption and Web3, co-built by hackers. Dora Dōjō regularly organizes and shares sessions in the form of live broadcasts, audio, and text. The topics covered include L1 and L2 consensus algorithms, architecture, and related content in GitHub repositories. Some of the specific topics covered include Scroll/Polygon zkEVM, Eigen's hybrid proof system, Starkware, Aztec, Optimism, Zcre, Aptus, Move, cryptography, including zero-knowledge proof, public key encryption, hash functions, and lattice ciphers, distributed systems, the Ethereum protocol stack, quantum computing and quantum information, and satellite communication and spacecraft system design. The Dora Dōjō community is constantly expanding and inviting new members to join. If you are interested in learning more about cutting-edge technologies and staying ahead of the curve, I encourage you to contact Dōjō at DoraDōjō0 on Telegram and claim your bounty. The Dōjō welcomes proposals for new content, and they will fund and share it. So, whether you are an experienced developer or just starting out, Dora Dōjō is the perfect community to learn and grow alongside like-minded individuals. Join us today and let's explore the world of cutting-edge technologies together. Ladies and gentlemen, welcome to an enthralling journey through the captivating realm of superconducting quantum circuits. We will explore the foundations, structure, and evaluation of these circuits, as well as the latest advancements and emerging directions within this field of study. So, fasten your seatbelts as we embark on this exciting adventure. Let's begin by diving into the workshop content we have lined up for today. Our first stop is an exploration of the basic principles of superconducting qubits. We'll take a stroll through the historical background of superconducting quantum computing, unearthing the key milestones that have led us to the present day. From there, we'll delve into the intricate structure and components that make up these remarkable superconducting quantum systems. We'll now shift our focus to the mesmerizing control and measurement of superconducting qubits. Buckle up as we witness the initial state preparation of these qubits, laying the groundwork for their quantum magic. We'll then unravel the art of manipulating the states of these superconducting qubits, where we can coax them into performing extraordinary computations and complex algorithms. Here are some background visuals of historical figures, visuals of scientists, and schematic diagrams that could be used on the control and measurement of superconducting qubits. First, John Bardeen, one of the inventors of the transistor. Second, Brian Josephson, who predicted the Josephson effect, which is essential for superconducting qubits. Third, David Wineland, who developed techniques for cooling and trapping atoms, which are used in some types of superconducting qubits. And here are some background visual schematic diagrams that could be used on the control and measurement of superconducting qubits. First, a diagram of a superconducting qubit circuit. Second, a diagram showing how the two possible states of the superconducting state can be used to represent the two possible values of a qubit. But that's not all. We'll also venture into the realm of reading out the states of superconducting qubits. Just like a skilled observer deciphering ancient hieroglyphics, we'll witness the innovative techniques and tools used to decode the quantum information stored within these delicate circuits. It's a fascinating process that brings us one step closer to harnessing the power of quantum computation. We've scratched the surface of the principles, design, and measurement of superconducting quantum circuits, while exploring the exciting developments and future trends that lie ahead. Let's dig deeper. we've spoken about overview an extraordinary expedition into the realm of superconducting qubits, where the laws of quantum mechanics intertwine with the wonders of superconductivity. Today, we embark on a quest to unravel the fundamental principles that underpin these remarkable qubits. So, fasten your seatbelts and prepare for a thrilling exploration into the basic principles of superconducting qubits. Our journey began with a glimpse into the historical background that paved the way for superconducting quantum computing. Over the years, brilliant minds and groundbreaking experiments have shaped the landscape of quantum technology. From the visionary ideas proposed by scientists like Richard Feynman and Paul Benioff to the groundbreaking discoveries of superconductivity, a foundation was laid for the development of superconducting qubits. Superconducting qubits are at the heart of superconducting quantum computing systems, enabling the manipulation and storage of quantum information. These qubits rely on the phenomenon of superconductivity, where certain materials, when cooled to extremely low temperatures, exhibit zero electrical resistance. This unique property allows for the creation of stable quantum states that can be manipulated and controlled with high precision. Here are some visuals illustrating superconducting materials and their properties. First, superconducting wire. A superconducting wire is a long, thin piece of material that has been cooled to a very low temperature and exhibits zero electrical resistance. Second, Josephson junction. A Josephson junction is a small, weak link between two superconducting materials. When a current is applied to a Josephson junction, it creates a quantum state known as a supercurrent. Third, magnetic field. A magnetic field can be used to manipulate the state of a superconducting qubit. By applying a magnetic field, scientists can change the energy levels of the qubit and make it easier or harder to flip its state. Fourth, cryogenic chamber. A cryogenic chamber is a special type of container that is used to cool materials to very low temperatures. Cryogenic chambers are essential for superconducting quantum computing systems, as they allow the qubits to operate at their optimal temperature. These are just a few examples of the many ways that superconducting materials and their properties can be used to create and manipulate quantum information. As scientists continue to develop new techniques and materials, superconducting quantum computing systems will become more powerful and capable. Now, let's take a closer look at the structure of superconducting quantum computing systems. These systems consist of various components meticulously engineered to create an environment conducive to quantum coherence. At the core of these systems, we find the superconducting qubits themselves, which are typically implemented using superconducting loops interrupted by Josephson junctions. The basic principles governing superconducting qubits revolve around the manipulation and measurement of their quantum states. One of the fundamental concepts is quantum superposition, which allows qubits to exist in multiple states simultaneously. This property gives superconducting qubits a tremendous advantage over classical bits and enables parallel processing and computation in quantum algorithms. Here is a video with an explanation of quantum superposition. Quantum superposition is a fundamental principle of quantum mechanics that allows a quantum object to exist in multiple states at the same time. This is in contrast to classical physics, where an object can only be in one state at a time. In the case of superconducting qubits, the two states that they can exist in are called 0 and 1. These states correspond to the two possible orientations of the qubit's spin. Here is a video with an explanation of quantum superposition. Quantum superposition is a fundamental principle of quantum mechanics that allows a quantum object to exist in multiple states at the same time. This is in contrast to classical physics, where an object can only be in one state at a time. In the case of superconducting qubits, the two states that they can exist in are called 0 and 1. These states correspond to the two possible orientations of the qubit's spin. The ability of superconducting qubits to exist in a superposition of states is what gives them the potential to revolutionize computing. By taking advantage of quantum superposition, superconducting qubits can be used to perform calculations that would be impossible on a classical computer. For example, a quantum computer could be used to factor large numbers, which is a problem that is currently considered to be too difficult for classical computers. This would have a major impact on the security of many online transactions, as it would make it much easier to break encryption codes. Quantum computers could also be used to design new drugs and materials, and to simulate complex systems such as the human brain. The possibilities are endless, and the development of superconducting qubits is one of the most exciting areas of research in science today. To manipulate and measure these quantum states, superconducting qubits rely on the precise control of external fields, such as microwave pulses and magnetic fields. By carefully tuning these parameters, we can manipulate the qubit states, perform quantum logic gates, and perform computations on quantum information. As you can see, the qubit is initially in a superposition of states. A microwave pulse is then applied to the qubit, which causes it to evolve into a different state. The state of the qubit is then measured, and the result is displayed on a screen. The process of qubit manipulation and measurement is very delicate. The microwave pulse must be applied with the correct amplitude and frequency, and the measurement must be performed with the correct sensitivity. If any of these parameters are off by even a small amount, the qubit state will be corrupted and the computation will fail. Despite the challenges, qubit manipulation and measurement are essential for performing quantum computations. By carefully controlling the qubit states, we can perform quantum logic gates, which are the basic building blocks of quantum computation. We can also perform computations on quantum information, which is the key to solving problems that are intractable with classical computers. The development of qubit manipulation and measurement techniques is a critical area of research in quantum computing. As the technology continues to develop, it is likely that qubit manipulation and measurement will become more precise and efficient. This will enable the development of more powerful quantum computers that can solve more complex problems. It's important to note that maintaining quantum coherence is a significant challenge. Superconducting qubits are sensitive to environmental noise and decoherence, which can disrupt the delicate quantum states. Ongoing research and engineering efforts are focused on mitigating these challenges and improving the coherence times of superconducting qubits. Another crucial principle is quantum entanglement, where the states of multiple qubits become correlated in such a way that the behavior of one qubit affects the others, regardless of the distance between them. This non-local relationship forms the basis for quantum communication and enables the potential for secure quantum networks. Quantum entanglement is a phenomenon in which the quantum states of two or more objects are linked together in such a way that they cannot be described independently of each other, even when the objects are separated by a large distance. This means that if you measure the state of one of the objects, you will instantly know the state of the other object, no matter how far away it is. This is in contrast to classical physics, where the state of an object can only be determined by measuring it. Quantum entanglement is a very strange phenomenon, and it is not fully understood by physicists. However, it is thought to be a fundamental property of nature, and it has the potential to revolutionize many areas of science and technology, including quantum computing, quantum communication, and quantum cryptography. One potential application of quantum entanglement is in quantum communication. Imagine that you have two entangled qubits, one in your possession and one in the possession of someone else who is very far away. If you measure the state of your qubit, you will instantly know the state of the other qubit, even though it is very far away. This could be used to send information between two parties in a very secure way, as it would be impossible for anyone else to intercept the message. Another potential application of quantum entanglement is in quantum cryptography. Imagine that you have two entangled qubits, one in your possession and one in the possession of someone else who you want to communicate with securely. You can use the entangled qubits to create a shared secret key, which can then be used to encrypt and decrypt messages. This would be much more secure than traditional encryption methods, as it would be impossible for anyone else to break the encryption without knowing the shared secret key. Quantum entanglement is a very promising area of research, and it is likely to have a major impact on many different fields in the years to come. We will delve into the intricate elements that make up these powerful quantum computing systems. So, fasten your seatbelts as we explore the fascinating world of superconducting quantum processors. Let's begin our journey by examining the key components that form the architecture of superconducting quantum processors. These processors are composed of interconnected elements that work together harmoniously to carry out quantum computations. So, let's dive in and explore these components in detail. Here is a visual of a superconducting quantum processor and its components. The key components of a superconducting quantum processor are qubits. Qubits are the basic units of information in a quantum computer. They are made of superconducting circuits that can be used to store and manipulate quantum information. Josephson junctions. Josephson junctions are tiny electrical switches that allow the qubits to be controlled. They are made of two superconducting electrodes separated by a thin insulating barrier. Control circuitry. This circuitry is used to apply microwave radiation to the qubits, which is used to control their state. Readout circuitry. This circuitry is used to measure the state of the qubits. It consists of a resonant circuit and a detector. Cooling system. This system is used to cool the qubits to a very low temperature, typically around 20 millikelvin. This is necessary to achieve quantum coherence, which is the ability of the qubits to exist in a superposition of states. These components are all interconnected on a chip, and they work together to carry out quantum computations. The qubits are used to store and manipulate quantum information. The Josephson junctions are used to control the qubits. The control circuitry is used to apply microwave radiation to the qubits. The readout circuitry is used to measure the state of the qubits. And the cooling system is used to keep the qubits at a very low temperature. The development of superconducting quantum processors is a rapidly growing field, and there are many different companies and research groups working on developing new and improved designs. As the technology continues to develop, superconducting quantum processors are likely to play an increasingly important role in many different areas, including quantum computing, quantum communication, and quantum cryptography. Then we move to explain the first vital component we encounter is the superconducting qubit. These remarkable building blocks lie at the heart of superconducting quantum processors. Fabricated using superconducting materials like aluminum or niobium, superconducting qubits take advantage of the unique properties of superconductivity to store and manipulate quantum information. Examples of superconducting qubits include transmon qubits, flux qubits, and Zeeman qubits. Here are some visuals of different types of superconducting qubits. Transmon qubits. Transmon qubits are the most common type of superconducting qubit. They are made of a small superconducting loop interrupted by a Josephson junction. The Josephson junction acts as a quantum gate, allowing the qubit to be manipulated in a controlled way. Flux qubits. Flux qubits are made of a superconducting ring threaded by a magnetic flux. The magnetic flux controls the state of the qubit. Zeeman qubits. Zeeman qubits are a type of transmon qubit that is optimized for high-frequency operation. They are made of a small superconducting loop with a small capacitance. The capacitance makes the qubit more sensitive to microwave radiation, which allows it to be operated at higher frequencies. These are just some of the different types of superconducting qubits that are being developed. The specific type of qubit that is used will depend on the application. For example, transmon qubits are often used for quantum computing, while flux qubits are often used for quantum communication. Superconducting qubits are a promising technology for quantum computing. They are relatively easy to manufacture, and they can be operated at very high frequencies. This makes them well suited for quantum computing applications that require a large number of qubits. However, superconducting qubits also have some challenges. They are very sensitive to noise, and they can be difficult to control. This makes it difficult to achieve long coherence times, which is essential for quantum computing. Despite these challenges, superconducting qubits are a promising technology for quantum computing. There is a lot of research being done to improve the performance of superconducting qubits, and it is possible that they will be able to overcome the challenges that they face. Moving forward, we discover the importance of qubit interconnectivity within these processors. Superconducting qubits are arranged in a two-dimensional grid-like structure, forming a network of interconnected qubits. Each qubit is coupled to its neighboring qubits, enabling the implementation of quantum gates and the execution of complex quantum algorithms. Here is a visual of the interconnected qubits in a grid-like structure. As you can see, the qubits are arranged in a two-dimensional grid. Each qubit is coupled to its neighboring qubits, which allows the qubits to be used to perform quantum computations. The coupling between the qubits is achieved using a variety of techniques, including capacitive coupling, inductive coupling, and direct electrical coupling. The coupling strength determines how strongly the qubits interact with each other. The strength of the coupling is important because it determines how difficult it is to implement quantum gates and the execution of complex quantum algorithms. If the coupling is too strong, the qubits will become entangled with each other, which can make it difficult to control them. If the coupling is too weak, the qubits will not be able to interact with each other, which will limit the types of quantum computations that can be performed. The optimal coupling strength is a trade-off between these two extremes. It is important to find a balance between the strength of the coupling and the ability to control the qubits. The development of qubit interconnectivity is a critical area of research in superconducting quantum computing. As the technology continues to develop, it is likely that qubits will be able to be interconnected in more complex ways, which will enable the development of more powerful quantum computers. There are another critical element in the architecture of superconducting quantum processors is the presence of microwave resonators, or cavities. These resonators serve as a medium for the coherent exchange of quantum information. They enhance the interaction between qubits and enable the transmission of microwave pulses that control and manipulate the qubit states. Examples of resonators include 3D cavities and coplanar waveguide resonators. Here are some visuals of microwave resonators and cavities. 3D cavities. 3D cavities are made of a three-dimensional structure of superconducting material. They are typically used for qubits that are operated at relatively low frequencies. And coplanar waveguide resonators. Coplanar waveguide resonators are made of a two-dimensional waveguide that is etched into a superconducting substrate. They are typically used for qubits that are operated at relatively high frequencies. Microwave resonators and cavities play an important role in superconducting quantum computing. They provide a medium for the coherent exchange of quantum information, which is essential for performing quantum computations. The resonators and cavities are used to control the qubits in a number of ways. For example, they can be used to apply microwave pulses to the qubits, which can be used to change their state. They can also be used to measure the state of the qubits. The development of microwave resonators and cavities is a critical area of research in superconducting quantum computing. As the technology continues to develop, it is likely that resonators and cavities will be able to be made smaller and more efficient, which will enable the development of more powerful quantum computers. Precise control and measurement electronics are essential for the functioning of superconducting quantum processors. These electronics play a pivotal role in manipulating and reading out the qubit states. Control electronics generate microwave pulses and magnetic fields that drive qubit transitions and perform quantum operations. Measurement electronics extract information about the qubit states using techniques like dispersive readout. Here is a visual of control and measurement electronics. As you can see, the control and measurement electronics are made up of a number of different components, including 1. Waveform generators. Waveform generators generate the microwave pulses that are used to control the qubits. 2. Amplifiers. Amplifiers amplify the microwave pulses so that they can be used to drive the qubits. 3. Magnetometers. Magnetometers measure the magnetic fields that are used to control the qubits. 1. Waveform generators. Waveform generators generate the microwave pulses that are used to control the qubits. 2. Amplifiers. Amplifiers amplify the microwave pulses so that they can be used to drive the qubits. 3. Magnetometers. Magnetometers measure the magnetic fields that are used to control the qubits. The control and measurement electronics work together to manipulate and read out the qubit states. The waveform generators generate the microwave pulses that are used to control the qubits. The amplifiers amplify the microwave pulses so that they can be used to drive the qubits. The magnetometers measure the magnetic fields that are used to control the qubits. The detectors measure the state of the qubits. The control and measurement electronics work together to manipulate and read out the qubit states. The waveform generators generate the microwave pulses that are used to control the qubits. The amplifiers amplify the microwave pulses so that they can be used to drive the qubits. The magnetometers measure the magnetic fields that are used to control the qubits. The detectors measure the state of the qubits. The control and measurement electronics are a critical part of superconducting quantum processors. They allow the qubits to be manipulated and read out, which is essential for performing quantum computations. Together, these components form a cohesive architecture within superconducting quantum processors, creating an environment where quantum computations can flourish. The interconnected qubits, coupled with microwave resonators, and supported by control and measurement electronics, pave the way for the execution of quantum algorithms and the exploration of quantum phenomena. Here is a visual that demonstrates the interaction and synergy between the components of a superconducting quantum processor. As you can see, the qubits are interconnected via microwave resonators. The control and measurement electronics are used to manipulate and read out the qubit states. The entire system is cooled to a very low temperature, typically around 20 millikelvin, to achieve quantum coherence. The interaction and synergy between these components is what allows superconducting quantum processors to perform quantum computations. The qubits are able to interact with each other via the microwave resonators. This allows them to be used to perform quantum gates, which are the basic building blocks of quantum computation. The control and measurement electronics allow the qubit states to be manipulated and read out, which is essential for performing quantum computations. The low temperature is necessary to achieve quantum coherence, which is the ability of the qubits to exist in a superposition of states. And with that, we conclude our captivating exploration of the architecture and components of superconducting quantum processors. We've uncovered the significance of superconducting qubits as the building blocks of these processors. We've witnessed the interconnected nature of qubits, the role of microwave resonators, and the importance of control and measurement electronics in driving quantum operations. The development of superconducting quantum processors is a rapidly growing field. There are many different companies and research groups working on developing new and improved designs. As the technology continues to develop, superconducting quantum processors are likely to play an increasingly important role in many different areas, including quantum computing, quantum communication, and quantum cryptography. Then after that, will unravel the critical factors that shape the design of these circuits, ensuring reliable and accurate quantum computations. So, let's dive into the world of quantum design considerations. Designing superconducting quantum circuits requires careful deliberation of several crucial factors. The first consideration on our list is coherence time and decoherence mitigation. Coherence time, the duration for which a qubit retains its quantum state, is of paramount importance in quantum computing. To mitigate the effects of environmental noise and decoherence, designers employ various techniques. Cryogenic enclosures and magnetic shielding are implemented to reduce external interference and prolong coherence times. Moving on, we encounter the essential concept of gate fidelity and error correction. Achieving high gate fidelity, the accuracy of quantum gate operations, is pivotal for precise computations. Designing qubits with low levels of intrinsic noise, optimizing control pulse shapes, and implementing error correction codes, such as surface codes, contribute to mitigating errors and improving the overall fidelity of quantum gates. Scalability and circuit complexity are also key design considerations in superconducting quantum circuits. As quantum computing progresses, the demand for larger numbers of qubits and more complex computations grows. Designers face the challenge of creating scalable architectures that can accommodate a higher number of qubits while addressing issues like crosstalk between qubits, maintaining qubit coherence in a larger system, and minimizing the number of control lines required. Now, let's shift our focus to the measurement and control systems for superconducting qubits. These systems play a crucial role in manipulating and extracting information from the qubits. Researchers employ various techniques to achieve precise control and measurement. This includes generating microwave pulses and magnetic fields for qubit manipulation, as well as extracting qubit state information through techniques like dispersive readout. Here is a visual of a measurement and control system for superconducting qubits. The measurement and control system works together to manipulate and read out the qubit states. The waveform generators generate the microwave pulses that are used to control the qubits. The amplifiers amplify the microwave pulses so that they can be used to drive the qubits. The magnetometers measure the magnetic fields that are used to control the qubits. The detectors measure the state of the qubits. The measurement and control system is a critical part of superconducting quantum computers. It allows the qubits to be manipulated and read out, which is essential for performing quantum computations. Here are some additional details about the measurement and control system. Waveform generators. Waveform generators are typically used to generate arbitrary waveforms. This allows the researchers to precisely control the qubit states. Amplifiers. Amplifiers are used to amplify the microwave pulses so that they can be used to drive the qubits. The amplifiers must be very precise, as even a small amount of error can corrupt the qubit state. Magnetometers. Magnetometers are used to measure the magnetic fields that are used to control the qubits. The magnetometers must be very sensitive, as they need to be able to measure very small changes in magnetic field. Detectors. Detectors are used to measure the state of the qubits. The detectors must be very sensitive, as they need to be able to measure very small changes in the qubit state. The development of measurement and control systems for superconducting qubits is a critical area of research in quantum computing. As the technology continues to develop, it is likely that measurement and control systems will become more precise and efficient. This will enable the development of more powerful quantum computers that can solve more complex problems. However, measurement and control in superconducting quantum computing present their own set of challenges. Environmental noise, qubit crosstalk, and limited measurement resolution can impact the accuracy and reliability of these processes. Researchers are actively working on developing solutions to overcome these challenges, improve the performance of superconducting qubits, and enhance the overall capabilities of quantum processors. And with that, we conclude our illuminating exploration of the key design considerations for superconducting quantum circuits. We've uncovered the significance of coherence time and decoherence mitigation, gate fidelity and error correction, as well as scalability and circuit complexity. Furthermore, we've touched upon the measurement and control systems employed in superconducting quantum computing, along with the challenges and solutions associated with these processes. Our presentation include on the challenges and solutions in measurement and control for superconducting quantum computing. Over the next 15 minutes, we will explore the obstacles faced in these crucial processes and delve into the innovative solutions that researchers are developing to overcome them. So, let's embark on this enlightening journey. The world of measurement and control in superconducting quantum computing is not without its challenges. The first challenge we encounter is noise and decoherence. Superconducting qubits are sensitive to environmental noise and decoherence, which can degrade the delicate quantum states. To combat this, researchers are developing techniques such as improved qubit designs, enhanced shielding from external noise sources, and implementing error correction codes. These measures mitigate the effects of noise and enhance the coherence of the qubits. Here are some visuals illustrating noise reduction techniques and error correction codes. Improved qubit designs. Researchers are developing new qubit designs that are more resistant to noise. For example, they are using materials that have less thermal noise, and they are designing qubits that are less susceptible to external magnetic fields. In enhanced shielding from external noise sources, Researchers are using better shielding to protect the qubits from external noise sources. For example, they are using cryogenic enclosures and magnetic shielding. And implementing error correction codes. Researchers are implementing error correction codes to correct for errors that are caused by noise. Error correction codes work by redundantly encoding the qubit state, so that even if some of the information is lost due to noise, the original state can be reconstructed. These techniques are all important for reducing the effects of noise and decoherence in superconducting quantum computing. As the technology continues to develop, it is likely that these techniques will become more effective and efficient. This will enable the development of more powerful quantum computers that can solve more complex problems. Here are some additional details about noise reduction techniques and error correction codes. Improved qubit designs. Improved qubit designs are one of the most promising approaches to reducing noise. By using materials that have less thermal noise, and by designing qubits that are less susceptible to external magnetic fields, researchers can significantly reduce the amount of noise that affects the qubits. Enhanced shielding from external noise sources. Enhanced shielding is another important approach to reducing noise. By using cryogenic enclosures and magnetic shielding, researchers can create a quiet environment where the qubits are less susceptible to noise. Implementing error correction codes. Error correction codes are a powerful technique for correcting errors that are caused by noise. By redundantly encoding the qubit state, error correction codes can ensure that the original state can be reconstructed, even if some of the information is lost due to noise. The development of noise reduction techniques and error correction codes is a critical area of research in quantum computing. As the technology continues to develop, it is likely that these techniques will become more effective and efficient. This will enable the development of more powerful quantum computers that can solve more complex problems. Our second challenge is crosstalk. When control signals intended for one qubit affect neighboring qubits, unwanted interactions and errors can occur. To address this, researchers are implementing isolation techniques, optimizing circuit layouts, and refining control sequences. These efforts minimize crosstalk, ensuring the fidelity and accuracy of operations. Here are some visuals demonstrating isolation techniques and optimized circuit layouts. Isolation techniques. Researchers are using isolation techniques to prevent control signals from affecting neighboring qubits. For example, they are using electrical isolation, optical isolation, and magnetic shielding. Optimized circuit layouts. Researchers are optimizing circuit layouts to minimize crosstalk. For example, they are using spacing techniques, routing techniques, and shielding techniques. These techniques are all important for minimizing crosstalk in superconducting quantum computing. As the technology continues to develop, it is likely that these techniques will become more effective and efficient. This will enable the development of more powerful quantum computers that can solve more complex problems. Here are some additional details about isolation techniques and optimized circuit layouts. Isolation techniques. Isolation techniques are a critical approach to minimizing crosstalk. By preventing control signals from affecting neighboring qubits, isolation techniques can ensure that the qubits are not corrupted by unwanted interactions. Optimized circuit layouts. Optimized circuit layouts are another important approach to minimizing crosstalk. By carefully designing the layout of the qubits and the control circuitry, researchers can minimize the chances of crosstalk occurring. Calibration and stability pose another critical challenge in measurement and control. High-precision control and measurement rely on accurate calibration and stable control and measurement systems. Researchers are developing calibration protocols, feedback mechanisms, and real-time monitoring techniques to ensure the stability of control parameters and improve the reliability of measurements. As we venture further, we encounter the challenge of scalability. Superconducting quantum computing aims to scale up to larger systems with a higher number of qubits. However, maintaining coherence and fidelity while scaling presents difficulties. Researchers are exploring solutions such as multiplexed readout, enabling simultaneous measurements of multiple qubits. Additionally, more efficient control architectures are being developed to facilitate the scalability of measurement and control systems. Measurement and control systems play a pivotal role in the success of superconducting quantum computing. Techniques such as dispersive readout, control pulse generation, flux biasing, and magnetic field control enable the manipulation and measurement of superconducting qubits. By addressing challenges related to noise, crosstalk, calibration, stability, and scalability, researchers are paving the way for improved performance and reliability of superconducting qubits, bringing us closer to the realization of practical and powerful quantum computers. And with that, we conclude our exploration of the challenges and solutions in measurement and control for superconducting quantum computing. We've unveiled the hurdles posed by noise, crosstalk, calibration, stability, and scalability, and discovered the innovative solutions that researchers are developing to overcome them. These advancements bring us closer to harnessing the full potential of quantum computing in our quest for knowledge and technological breakthroughs. We now move on to an important aspect of our discussion, the interpretation of the schematic diagram of a transmon qubit and the calibration of readout results for quantum bit states. The schematic diagram represents the physical implementation of a quantum bit, or qubit, which serves as the fundamental unit of quantum information. Let's delve into the key components and their significance. At the heart of the transmon qubit lies a superconducting island, formed by a loop of superconducting material. This island connects to two electrodes known as Josephson junctions, also made of superconducting material. These Josephson junctions play a crucial role in controlling and manipulating the quantum state of the qubit. In addition, the schematic diagram includes a capacitor represented by 3 parallel lines and an inductor represented by the coil. To better understand the calibration of readout results, it's important to grasp the concept of initializing the qubit and reading its state. The qubit can be initialized to either the ground state or the excited state by applying a microwave pulse. The readout is achieved by measuring the current through the Josephson junction. The transmon qubit operates in a regime where the Josephson junctions intentionally possess high capacitance, reducing its sensitivity to charge noise and allowing for longer coherence times. Furthermore, the qubit is coupled to a microwave resonator, which enables control and measurement of the qubit's state. As we progress through the workshop, we come across the challenges involved in calibrating the readout results of quantum bit states. Let's explore these challenges together. The qubit can exist in a superposition of the ground and excited states, making it challenging to determine its true state. The readout process itself introduces noise, further complicating the accurate determination of the qubit's state. The calibration process can be time-consuming and resource-intensive. Despite these challenges, calibrating the readout results of quantum bit states is a crucial step in improving the accuracy and reliability of quantum computing devices. Begin by initializing the qubit to a known state, typically the ground state or a superposition state. Measurement pulse calibration: apply a series of measurement pulses to the qubit, adjusting their duration, amplitude, and other parameters to obtain clear and distinguishable signals corresponding to different qubit states. Discrimination threshold determination: set a discrimination threshold that optimally differentiates between the qubit being in the ground state or an excited state, based on the measured signals, accounting for noise and imperfections. Characterization and correction: employ additional techniques to enhance readout accuracy, such as analyzing the readout system's response to different qubit states and implementing algorithms to mitigate errors and correct for biases. Feedback loop: optional, establish a feedback loop to continuously adjust the readout parameters based on measurement results, ensuring ongoing accuracy and reliability. In summary, calibrating the readout results of quantum bit states involves fine-tuning measurement pulses, setting a discrimination threshold, characterizing the readout system, and implementing corrective measures. These endeavors aim to ensure the precise determination of the qubit state and enhance the accuracy of quantum computing. Thank you for joining us in this elucidating presentation on the interpretation of the schematic diagram of a transmon qubit and the calibration of readout results for quantum As we conclude our exploration of superconducting quantum computing, let's recap the key concepts, highlight the significance and potential applications of superconducting quantum computers, and summarize the current research progress and future directions. Throughout our discussion, we delved into fundamental concepts that form the foundation of superconducting quantum computing. We examined different types of superconducting qubits, their working principles, and the importance of coherence, gate operations, and readout techniques. We also explored the design, preparation, and measurement of superconducting quantum circuits, emphasizing the historical background, structure of superconducting quantum computing systems, and measurement and control systems for superconducting qubits. Superconducting quantum computers hold tremendous significance in unlocking new possibilities and applications across various fields. Their potential impact spans areas such as optimization and simulation, where they can revolutionize materials science, drug discovery, and financial modeling. Additionally, superconducting quantum computers offer enhanced security through quantum cryptography algorithms, and they have the potential to accelerate machine learning and artificial intelligence algorithms. In recent years, the field of superconducting quantum computing has made significant research progress. Milestones such as quantum supremacy and improved coherence times have showcased the potential of these systems. Advances in superconducting qubit technologies, including novel designs and error correction techniques, have paved the way for more reliable and scalable quantum computing systems. However, challenges and limitations remain. Coherence and decoherence issues, scalability concerns, and control complexity pose ongoing obstacles that must be addressed to further advance the field. Looking ahead, future research directions include improving coherence and error correction techniques, exploring hybrid quantum systems, and developing scalable qubit architectures. These efforts aim to bring us closer to practical and fault-tolerant superconducting quantum computing systems, capable of solving complex problems and transforming various industries. Superconducting quantum computing holds immense promise for revolutionizing computing and solving problems beyond the capabilities of classical systems. With continued research, technological advancements, and collaborative efforts, we are paving the way towards a future where the power of quantum information can be fully harnessed to unlock unprecedented possibilities. Next, I will move to referring to several key references that provide valuable insights into this topic. Let's dive in. The first reference is a groundbreaking study by Barnes et al. Published in Nature in 2014. In their work, the researchers demonstrated superconducting quantum circuits that operate at the surface code threshold for fault tolerance. This is a significant achievement as it opens up possibilities for building fault-tolerant quantum computers. Moving on, the second reference by Devoret and Skolkoff, published in Science in 2013, offers an insightful outlook on superconducting circuits for quantum information. They discuss the current state of the field and highlight the potential for advancements in quantum computing using superconducting qubits. For a comprehensive guide to superconducting qubits, the reference by Krantz et al. In Applied Physics Reviews, 2019, is invaluable. It provides practical information for quantum engineers, discussing the different aspects of superconducting qubits and their implementation. One of the most significant achievements in the field of superconducting quantum computing is quantum supremacy, which was demonstrated by Arut et al. In 2019. Their work, published in Nature, describes the use of a programmable superconducting processor to achieve quantum supremacy, marking a major milestone in quantum computing. To gain a broader understanding of the current state of superconducting qubits, the reference by Kjaergaard, Kringhage, and Malmer in the Annual Review of Condensed Matter Physics, 2020, is highly recommended. It provides an overview of the latest developments and research progress in the field. Wendin and Shimiko's review article in Reports on Progress in Physics, 2017, is an excellent resource for understanding the theory and experimental aspects of superconducting quantum circuits. It offers a comprehensive overview of the field, discussing various theoretical concepts and experimental techniques. The next reference, a Nature paper by Kelly et al., 2015, focuses on state preservation through repetitive error detection in superconducting quantum circuits. The researchers propose a method to mitigate errors and preserve quantum states, which is crucial for reliable quantum computation. Another noteworthy study published in Science by Nig et al., 2014, explores quantum computations on a topologically encoded qubit in superconducting circuits. The researchers investigate the robustness and potential of topological protection for error correction in quantum computing. In their Nature Communications paper, Rist et al., 2015, present a method for detecting bit flip errors in logical qubits using stabilizer measurements in superconducting quantum circuits. Their work addresses an important challenge in quantum error correction, paving the way for improved error detection strategies. Lastly, the reference by Gambetta et al. In Physical Review A, 2011, introduces the quantum trajectory approach to circuit QED. This work explores quantum jumps and the Zeno effect in the context of superconducting quantum circuits, providing valuable insights into the dynamics and control of quantum systems. These 10 references collectively cover a wide range of topics in superconducting quantum computing, including fault tolerance, circuit implementation, quantum supremacy, error detection, and dynamics. They represent significant contributions to the field and serve as valuable resources for further exploration. Thank you for your attention. I hope that these references and the information presented today will enhance your understanding of superconducting quantum computing. I am now open to any questions you may have. I would like to take a moment to express my sincere gratitude to each and every one of you for attending my presentation on superconducting quantum computing. Your presence here today means a great deal to me, and I truly appreciate your time and interest in this fascinating topic. I would also like to extend my heartfelt thanks to Dora Dōjō and Dora Hack, who provided me with this wonderful opportunity to share my knowledge and insights with all of you. Their support and guidance throughout the preparation process have been invaluable. Furthermore, I want to acknowledge the contributions of the researchers and authors whose work I referenced in my presentation. Their dedication, innovative thinking, and countless hours of research have paved the way for advancements in superconducting quantum computing. In closing, I want to reiterate my deepest appreciation to each and every one of you for being a part of this presentation. Your presence and engagement have made it a truly memorable experience for me. Thank you once again for your time, attention, and support.